And if humanity was reset 20 times, Earth, a planet that has witnessed the birth and death of civilizations, entire species, empires of life that arose from the cosmic dust, only to return to it. But there is a story they never told you in school, a secret buried in layers of sediment and fragments of forgotten bones. We were not the first, we were not the only ones, and perhaps, just perhaps, we will not be the last. Imagine for a moment that you could travel back in time, not thousands of years, but millions. You would see something extraordinary, something that defies everything you thought you knew about our species. You would see 20 different types of humans walking on this planet, 20 branches of the tree of life, each with its own way of thinking, of hunting, of loving, of surviving. Some were giants compared to us, others as small as children. Some mastered fire almost 2 million years ago. Others developed brains as large as ours, perhaps even superior in some capacities, and all of them disappeared. One by one, like candles extinguished in the darkness, these humanities became extinct. Some left behind barely a handful of fossilized bones. Others, only genetic ghosts hidden in our own DNA. There are species of which we only know a finger, a fragment of a jawbone, microscopic strands of genetic material extracted from remote caves in Siberia. And yet, they existed. They laughed. They cried. They feared death. They looked at the same stars you look at now and wondered what it all meant. Why did they disappear? Was it the climate that changed too fast? Were they diseases that swept across entire continents? Or was it us, Homo sapiens, who walked over their graves while building our empire? Science has theories, but the complete truth remains shrouded in the deepest mystery humanity has ever faced, the mystery of our own existence. There is evidence of encounters. Neanderthals and sapiens not only met, they mated, exchanging genes that you still carry in your body at this very moment. Denisovans left their genetic footprint in populations of Asia and Oceania, living proof that our ancestors not only coexisted with other human species, but interbred with them. But then, abruptly, silence. 40,000 years ago, the Neanderthals disappeared. 30,000 years ago, other species vanished, and suddenly, only we remained. Are we the survivors of a brutal competition for resources, the accidental winners of an evolutionary lottery, or something darker, something we prefer not to examine too closely? The latest archaeological discoveries paint a disturbing picture. Sapiens tools, found in the same stratigraphic layers where the Neanderthals disappear. Evidence of interspecies violence. Extinction patterns that follow our migratory movements like a deadly shadow. But this is not just a story of death and extinction. It is a story of incredible diversity, of evolutionary experiments that tested every possible path to intelligence. It is the story of Homo floresiensis, child-sized humans who hunted pygmy elephants on remote islands of Indonesia and survived until barely 50,000 years ago. It is the story of Homo naledi, discovered only in 2015, who buried their dead in deep underground burial chambers, a behavior we believed exclusive to species with much larger brains. It is the story of Homo erectus, the tireless traveler who conquered 3 continents and dominated Earth for almost 2 million years, longer than any other human species, including us so far. And it is the story of species so mysterious that we barely know their names. Homo luzonensis, Homo georgicus, the Red Deer Cave people. Each one is a lost chapter in the book of our history. On Datoterra, we explore these forgotten mysteries, these buried secrets that science is only beginning to unearth. Because understanding where we come from is not just academic curiosity. It is understanding what makes us human, what made us survive when so many others failed, and what awaits us in the future. The following chapters will take you on a journey through millions of years. You will meet your distant cousins, species that shared this planet with us and then disappeared into the mist of time. You will discover that the history of humanity is not a straight line from simplicity to complexity, but a leafy tree with branches that extended in all directions, most of them abruptly cut before reaching their full potential. And at the end of this journey, you will face the most uncomfortable question of all. If 20 different human species have already disappeared, if 99% of all species that ever existed are now extinct, what makes us think that we will be different? Are we really the endpoint of human evolution, or simply another branch, waiting its turn to wither and fall? The answer may be closer than you imagine, and you may not like what we discover together. For decades, textbooks taught us a simplified lie. They showed us illustrations of an orderly line, a hunched ape that gradually straightened, lost hair, gained intelligence until it became the modern human. A clean progression, a direct arrow from the primitive past to the civilized present. The reality is infinitely more chaotic, more fascinating, and much more unsettling. The truth is that human evolution was not a ladder, it was an explosion, a family tree so dense and tangled that scientists are still trying to unravel its branches. And what they have discovered in the last 2 decades has completely revolutionized our understanding of who we are and where we come from. Imagine Africa 7 million years ago. The continent is undergoing dramatic climatic changes. The tropical forests that covered vast expanses begin to recede, replaced by open savannas. In this new world, our ape ancestors face a crucial evolutionary decision: stay in the shrinking trees or venture out onto the open plains. Some chose to stay and became the ancestors of modern chimpanzees and gorillas. Others took the most momentous step in the history of life on Earth. They descended from the trees and began to walk upright. That simple change, walking on 2 legs instead of 4, triggered a cascade of evolutionary transformations. The hands, freed from the need to support the body, were able to specialize in manipulating objects. The brains, receiving new challenges from navigation and survival in open terrain, began to expand. And so, approximately 6 or 7 million years ago, the first hominins were born, the first members of our evolutionary family. But here is the crucial detail that changes everything. These first hominins did not evolve into a single species. Evolution, in a phenomenon that biologists call adaptive radiation, took that basic bipedal primate design and modified it in 20 different ways. Each modification was an experiment, an evolutionary gamble on a different survival strategy. Some of these experiments bet on larger brains, others on stronger jaws, capable of chewing hard foods during droughts. Some developed robust and muscular bodies, perfect for cold climates. Others became slender and agile, adapted for running long distances under the African sunday. There were species that never left the forests, others that conquered the mountains, and some that crossed oceans on natural rafts to colonize remote islands where they evolved in completely unexpected directions. For millions of years, these species coexisted, not necessarily in peaceful harmony, but sharing the same planet, sometimes the same territories. Fossil records show that 2 million years ago, in East Africa, at least 4 different human species lived in the same geographical region. 4 types of humans, each with its own way of life, its own tools, its own strategies for facing the dangers of an unforgiving world. Think about that for a moment. 4 intelligent, self-aware species sharing the same landscape. Did they see each other as distant cousins or as dangerous competitors? Did they trade ideas and technology, or did they carefully avoid each other? Scientists have found evidence of both behaviors: archaeological sites where different species clearly exchange tools and techniques, and others where settlement patterns suggest aggressive territoriality and mutual exclusion. The exact number of human species that have existed is the subject of intense scientific debate. Some researchers count 18 distinct species. Others raise the number to 23, or even more. The discrepancy arises from a fundamental question that plagues paleontology. How much physical difference is needed to declare two fossils as separate species? A Homo sapiens from 50,000 years ago looked different from a modern human, but we are still the same species. So, how do we know if two skulls from 1,000,000 years ago belong to different species or simply to populations with normal variations? Despite these uncertainties, there is a solid consensus on at least 15 clearly distinct human species, and every year, new discoveries add more names to the list. In 2003, Homo floresiensis shook the scientific world. In 2010, the Denisovans were identified solely from DNA. In 2015, Homo naledi emerged from the depths of a South African cave, and in 2019, Homo luzonensis joined the family from a remote island in the Philippines. Each new discovery complicates the picture, but it also enriches it. It shows us that the history of humanity is much older, more diverse, and more complex than we ever imagined. We are not the inevitable product of millions of years of progress. We are the improbable survivors of a brutal process that eliminated 19 out of every 20 evolutionary experiments in advanced intelligence. The chronology is astonishing. The first hominins walked 7 million years ago. The first stone tools appeared 3,300,000 years ago, long before the genus Homo existed. For almost 2 million years, multiple species coexisted, each carving out its own ecological niche. But approximately 400,000 years ago, something changed. Species began to disappear at an accelerated rate. 300,000 years ago, probably fewer than 10 human species remained. 100,000 years ago, maybe 5. 50,000 years ago, only 3 or 4. And 30,000 years ago, only us. Homo sapiens remained alone on a planet that once harbored an incredible diversity of humanities. What caused this massive collapse? Why did such a robust and diverse family tree suddenly shrink to a single branch? The answers are not simple, and as you will discover in the following chapters, they are likely different for each extinct species. Climate played a huge role. The last 2 million years have been a climatic roller coaster of brutal ice ages, alternating with warm periods. Each climate change reshaped landscapes, moved resources, and forced massive migrations. Species that could not adapt quickly enough simply became extinct, their ecological niches disappearing under layers of ice or transforming into inhospitable deserts. But climate does not explain everything. Some species survived multiple glacial cycles, only to disappear during a relatively stable period. This is where the story becomes darker and harder to accept, because many of these extinctions occurred precisely when Homo sapiens arrived in new regions. There is no conclusive evidence of deliberate genocide, but it is not necessary either. When a more efficient hunting species arrives in a territory, it can deplete resources quickly enough to doom less efficient species to starvation. When a species brings new diseases to which others have no immunity, epidemics can sweep away entire populations without anyone throwing a single spear. And when two species compete for the same limited resources, the more adapted one always prevails, without the need for direct conflict. Homo sapiens had advantages, not necessarily bigger brains, because Neanderthals were equal to us in that respect. But we had something more, a unique capacity for large-scale social cooperation, for complex symbolic communication, for rapid technological innovation. These seemingly small advantages turned out to be the difference between survival and extinction. The human family tree is a humbling reminder. It shows us that we are not the inevitable pinnacle of evolution. We are simply the lucky ones, the ones who were in the right place, at the right time, with the right adaptations. Our cousins had an equal right to inherit the earth. Some were stronger, others probably just as intelligent, but all shared the same ultimate fate. They disappeared into the dust of time, leaving only fragments of bones and tools as silent evidence that they once walked under the same Sunday. And now, after 30,000 years of solitude as the sole human species on the planet, we are discovering that we are not as alone as we thought, because although these species disappeared physically, some left behind something more lasting, their DNA interwoven with ours, genetic ghosts that continue to influence who we are today. Let's go back 4 million years. The Earth is an unrecognizable place. East Africa is literally fracturing, the Great Rift Valley tearing the continent like a gigantic geological wound. Volcanoes spew ash into the sky. The tropical forests fragment into green islands surrounded by increasingly expansive grasslands. And in this transforming world, the first creatures we might recognize as remotely human appear: the Australopithecines. The name literally means southern ape, and for decades after their discovery, scientists debated whether they truly deserved to be called human or were simply apes with an unusual upright posture. The answer, as is often the case in evolution, is complicated. They were both. They were neither. There was something in between, an evolutionary experiment that lasted 3 million years, much longer than Homo sapiens has existed so far. The first Australopithecus was discovered in 1924 in South Africa, a small skull found in a limestone quarry. But it was in 1974 when the world truly met these forgotten ancestors. A team of paleontologists in Ethiopia unearthed a partial skeleton of a female who lived 3,200,000 years ago. They named her Lucy after the Beatles' song playing in their camp that night, and Lucy changed everything. For the first time, we had complete skeletal evidence of how these early hominins walked. Lucy measured barely 1 meter and 6 centimeters in height. She weighed around 29 kilograms. She had a brain the size of a grapefruit, approximately 450 cubic centimeters, less than a third the size of the modern human brain. Her skull looked decidedly ape-like, with a low forehead, forward-projecting jaws, and no chin, but her legs, her hips, the shape of her pelvis, all screamed an undeniable truth. Lucy walked upright. And not just Lucy. Her species, Australopithecus afarensis, dominated East Africa for almost 1 million years, but they were not alone. The fossil record reveals at least 8 different species of Australopithecines that lived between 4 million and 2 million years ago. Some were gracile, slender, and agile. Others were robust, built like fighters with massive jaws and bony crests on their skulls, where extraordinarily powerful chewing muscles anchored. This diversity tells us something fascinating about early human evolution. Australopithecines were experimenting with different survival strategies. The gracile species like Lucy probably ate a varied diet of fruits, tender leaves, insects, and occasionally meat from small animals. They were generalists, adaptable, capable of changing their eating habits according to the season and the availability of resources. The robust species bet on a different strategy. Australopithecus, robustus, and Paranthropus, boisei, developed chewing apparatus capable of crushing hard seeds, roots, and fibrous vegetation that other species could not process. Their molars were enormous, the size of marbles, with enamel as thick as armor. When other hominins went hungry during droughts, These specialized chewers could survive by eating foods no one else wanted. But this specialization came at a cost. When the climate changed dramatically, approximately 2 million years ago, when Africa became even drier and the plants they depended on began to disappear, these specialists could not adapt quickly enough. One by one, the robust Australopithecines became extinct, their ecological niches disappearing under the relentless pressure of climate change. However, the gracile Australopithecines had other problems. They were small, vulnerable, and lived on a continent teeming with lethal predators: saber-toothed lions, giant hyenas, the size of bears, leopards, wild dogs, eagles large enough to carry away an Australopithecine child. The fossil record is full of Australopithecine bones, with predator teeth marks, skulls punctured by the talons of birds of prey. Brutal evidence that these early hominins were not at the top of the food chain, they were prey. The life of an Australopithecus was short and dangerous. Studies of dental wear and bone growth suggest that most died before reaching 20 years of age. Adult females probably spent much of their lives pregnant or caring for young. Males competed fiercely for access to females, as evidenced by the dramatic size differences between the sexes. A male Australopithecus afarensis could be almost double the size of a female, a sexual dimorphism that suggests societies where dominant males monopolized reproduction. They lived in small groups, probably between 20 and 50 individuals, constantly moving in search of food and water. During the day, they walked the open savannas, collecting what they could find. At night, they climbed trees to sleep, escaping terrestrial predators that hunted in the darkness. Their arms were still long and powerful, perfectly adapted for climbing, evidence that they never completely abandoned the refuge of the trees. They did not use tools, at least not stone tools that could fossilize, but that does not mean they were simple. Modern chimpanzees use sticks to extract termites, stones to crack nuts, leaves as sponges to drink water. Australopithecines probably did the same and more. But wood rots, leaves disintegrate, and after 3 million years, nothing remains but the bones and teeth. For decades, scientists assumed that the Australopithecines were our direct ancestors, a necessary rung on the ladder toward modern humanity. But the most recent discoveries paint a more complicated picture. It turns out that several species of Australopithecines coexisted with the first members of the genus Homo. For hundreds of thousands of years, these two evolutionary branches shared the same landscape. The Australopithecines clinging to their ancient way of life, while their more cerebral cousins began to experiment with something revolutionary: stone tools. The question that torments paleontologists is simple but profound. Why did the Australopithecines disappear? They survived for 3 million years, adapting to brutal climatic cycles, dodging predators, expanding across much of Africa. And then, approximately 2 million years ago, all species simply became extinct. None remained. Theories abound. Some scientists point to climate change. 2 million years ago, Earth entered a period of extreme climatic fluctuations, with increasingly severe ice ages. The forests receded even further. The savannas expanded. Water sources became less predictable. Australopithecines, with their small brains and limited cognitive capacities, simply could not adapt quickly enough. Other researchers suggest direct competition with early Homo. When species with larger brains appeared, capable of making stone tools and processing meat more efficiently, the Australopithecines lost their advantage. In the struggle for limited resources, the more intelligent hominins always won, not necessarily through direct violence, although that may also have occurred, but simply by being more efficient, exploiting resources more quickly, leaving less for the others. And, There is a third, more intriguing and more unsettling theory. Perhaps the Australopithecines did not really disappear. Perhaps they evolved. Perhaps at least one of the gracile Australopithecine species was the direct ancestor of Homo habilis, the first member of our genus. In that case, they did not become extinct. They simply transformed into something different, something with a larger brain and more advanced capabilities. But even if that is true, the majority of Australopithecine species did disappear without descendants. The robust Australopithecines definitely became extinct without leaving heirs, and with them went the first great evolutionary experiment in bipedalism, nature's first attempt to create a creature that could walk upright while maintaining the ability to live in trees. The legacy of the Australopithecines is undeniable. They gave us bipedalism, the liberation of the hands, the first step toward complex tool manipulation. They showed us that it was possible to survive in the open savannas, without claws, without fangs, without venom, only with cunning and social intelligence. They set the evolutionary stage for everything that came next. But they also taught us a darker lesson. They showed us that evolutionary success, even success that lasts millions of years, does not guarantee permanent survival, that species that dominate their era can completely disappear when conditions change, that 3 million years of successful adaptation can end in extinction when a more efficient competitor appears or when the climate changes too quickly. Lucy died 3,200,000 years ago, probably falling from a tree and fracturing multiple bones. Her skeleton remained in the mud of a river until erosion exposed it, and a team of scientists found it in 1974. For 3 million years, she rested in the African soil, waiting for someone to discover her and tell her story. And now we, her distant descendants, look at her bones in museums and try to imagine what her world was like. We try to understand what it feels like to walk upright but sleep in the trees. What it feels like to have consciousness but not complex language. What it feels like to be human but not quite. The Australopithecines were the first to fall, but they would not be the last. 2,800,000 years ago, something extraordinary happened on the shores of a lake in East Africa. Someone picked up a stone, deliberately struck it against another, and created the first object intentionally designed by a conscious mind. It was not an accident, it was not instinct, it was thought transformed into action. Imagination turned into physical reality. It was the birth of technology. That someone was probably Homo habilis, the handy man, the first member of our genus Homo. And with that first stone tool, everything changed. Human evolution stopped, depending solely on random genetic mutations and slow biological adaptations. Now knowledge could be transmitted from generation to generation, improved, refined. Culture became an evolutionary engine as powerful as the genes themselves. But before celebrating this triumph, we need to understand something crucial. Homo habilis existed for barely 600,000 years. That may sound like a long time, but in evolutionary terms, it is a blink of an eye. The Australopithecines lasted 3 million years. Homo erectus would dominate for almost 2 million. Even the Neanderthals survived more than 300,000 years. But Homo habilis, the first craftsman, the one who opened the Pandora's box of technology, disappeared almost as quickly as he appeared. The first fossils of Homo habilis were discovered in 1960 in the Olduvai Gorge, Tanzania, by the legendary team of Louis and Mary Leakey. The finding caused immediate controversy. Some scientists argued that these fossils were not different enough from the Australopithecines to merit a new genus. Others insisted that the increase in brain size from 450 cubic centimeters in Australopithecines to 650 cubic centimeters in Homo habilis, represented a fundamental evolutionary leap. The debate was partially resolved when scientists found stone tools alongside the fossils. Simple tools, certainly sharp flakes created by striking one stone against another, what archaeologists call Oldowan technology, but tools nonetheless. And the association between these fossils and these tools convinced the scientific community that they were indeed looking at something new, something that deserved to be called Homo, or human. Homo habilis did not look particularly impressive. Approximately 1.3 meters tall and weighing around 32 kilograms, they were barely larger than the Australopithecines. Their arms were still long, suggesting they spent considerable time in the trees. Their jaws were still large and projecting, although less so than their ancestors. But their brain, that critical organ, was almost 50% larger than that of any Australopithecus. What could you do with that bigger brain? Apparently quite a lot. Homo habilis tools show an understanding of basic geometry. To create a sharp edge, you need to strike a stone at the correct angle with the correct force. You need to visualize the result before acting. You need planning, foresight, an understanding of cause and effect. These are cognitive capacities that no Australopithecus demonstrated possessing, and they used them for something revolutionary: meat processing. Homo habilis archaeological sites are full of animal bones with cut marks, clear evidence that they used their stone tools to strip flesh from carcasses. They were not efficient hunters yet. They were probably mainly scavengers, arriving after large predators fed and using their tools to access the remains that other carnivores could not utilize. But even scavenging required intelligence. You needed to find the carcasses before they rotted, avoid the predators that might still be nearby, and work quickly to extract the meat before hyenas or vultures chased you away. And then there was the problem of digestion. Unlike true carnivores, hominins do not have digestive systems designed for raw meat, but meat provided dense calories, essential proteins, critical nutrients to fuel hungry brains. Here we find one of the most fascinating paradoxes of human evolution. Larger brains require more energy. A modern human brain consumes approximately 20% of the body's total calories, despite accounting for only 2% of the body mass. For the brains of Homo habilis to grow, they needed more calorically dense food sources. Meat provided those calories, but to obtain meat efficiently, they needed larger brains to create tools and develop scavenging strategies. It is a positive feedback loop. Larger brains allow for better food acquisition, which allows for even larger brains, which allows for more advanced technology, which allows for even richer diets. And once this cycle began, it accelerated human evolution at an unprecedented rate in the history of life on Earth. But Homo habilis did not live alone in East Africa. The fossil record shows multiple species coexisting in the same region. Robust Australopithecines were still chewing their hard seeds. Other Homo species were beginning to appear. And all these hominins competed for the same limited resources in an increasingly arid and challenging environment. The competition must have been brutal. Archaeological sites show evidence of occasional violence among hominins. Skulls with healed fractures, indicating non-lethal but significant aggression. Bones with marks that could be from cannibalism, although this is highly debated. What is certain is that multiple hominin species with similar capacities could not occupy exactly the same ecological niche indefinitely. Something had to give, and what gave was Homo habilis. Approximately 1,400,000 years ago, they disappeared from the fossil record, not gradually, but relatively abruptly in geological terms. One moment they were there, creating their simple tools, scavenging on the African savannas. The next, they were gone, replaced by more advanced Homo species with even larger brains and more sophisticated tools. Theories about their extinction are speculative but logical. They were likely surpassed by their own evolutionary descendants. Homo erectus appeared approximately 2 million years ago, and these new humans were superior in almost every way. Taller, stronger, with even larger brains, capable of making more advanced tools. In any direct competition for resources, Homo erectus would win. But there is another, more intriguing possibility. Perhaps Homo habilis did not really become extinct. Perhaps they evolved so quickly that their descendants became so different that we classify them as separate species. In that scenario, Homo habilis did not die. They simply transformed into something better adapted, something more intelligent, something more capable of surviving in an increasingly competitive world. The problem with this theory is that the fossil record shows a gap. There is a period where Homo habilis disappears and other Homo species are already established, without clear intermediates connecting them. That could simply be an artifact of fossil preservation. Most organisms never fossilize, but it could also indicate real extinction, followed by replacement by species that evolved in other regions of Africa. What makes the story of Homo habilis particularly tragic is the unrealized potential. They were the first to cross the threshold into true humanity. The first to demonstrate that intelligence and technology could compensate for the lack of claws and fangs. The first to show that the future would belong not to the physically strongest, but to the mentally cleverest. But they did not live long enough to see that future realized. They did not live to see their evolutionary descendants conquer continents, domesticate fire, develop complex language, create art and music, and civilization. They were pioneers who died on the frontier, opening paths that others would follow, but which they would never fully traverse. Their stone tools remained scattered across the African landscapes, silent witnesses to the first awakening of human technological consciousness. Every sharp flake is evidence of a moment when someone imagined something that did not exist and then created it. Every archaeological site is a reminder that 2 million years ago, our ancestors took the first tentative step toward becoming the species that would dominate the planet. But they are also reminders of fragility, that being the first to innovate does not guarantee being the last to survive. That opening a revolutionary path does not mean you will be the one to walk to the end of that path. Homo habilis was the first craftsman, but others would perfect the art. If you had to choose the most successful human species that ever existed, the answer would not be Homo sapiens. It would only be us, if we survive another 1.5 million years. Because that record belongs to Homo erectus, the upright man, a species that dominated Earth for almost 2 million years, from approximately 1,900,000 years ago until barely 100,000 years ago. No other hominin species even comes close to that astonishing longevity. Homo erectus was the first true traveler, the first hominin to leave Africa and colonize new continents, the first to master fire consistently, the first to develop standardized tools that remained virtually unchanged for more than 1 million years. And possibly, although this is more speculative, the first to develop something akin to spoken language. The first Homo erectus fossils were discovered in 1891 in Java, Indonesia, by a Dutch doctor named Eugène Dubois. At that time, the idea that humans had evolved was so controversial that Dubois faced ridicule and fierce skepticism. They called him the Java Man, and for decades, scientists debated what he actually was. Some argued he was a primitive human ancestor. Others insisted he was simply a modern human deformed by disease. It was not until the early 20th century, when more similar fossils appeared in China, near Beijing, in the 1920s and 30s. In the 50s and 60s, Africa revealed even older specimens, and gradually, it became impossible to deny the truth. Homo erectus had been real, had been successful, and had been everywhere. Physically, Homo erectus represented a massive evolutionary leap. Approximately 1.75 meters tall, they were as tall as many modern humans. Males weighed around 68 kilograms, females about 55. Their brain averaged 900 cubic centimeters, almost 50% larger than Homo habilis, although still significantly smaller than the 1,400 cubic centimeters of the modern sapiens brain. But the most important thing was their body. For the first time in human evolution, we have a species completely adapted to terrestrial life. The arms were no longer disproportionately long. The legs were long and straight, perfect for walking and running long distances. The pelvis and spine showed adaptations to support vertical weight for prolonged periods. Homo erectus had completely abandoned the trees. There was no more refuge in the branches. All their survival depended on their intelligence and their ability to move constantly, and move they did. The expansion of Homo erectus out of Africa is one of the most astonishing events in the history of life. Approximately 1,900,000 years ago, they began to appear in Georgia, on the borders of Europe and Asia. 1,800,000 years ago, they were in Java. 1,700,000 years ago, they had reached China. In less than 200,000 years, a species that had evolved in the African savannas had colonized most of Asia and parts of Europe. How did they achieve it? First, they were exceptional walkers. Biomechanical studies of their skeletons show that they could walk 20 or 30 kilometers a day without excessive effort. Second, they were adaptable omnivores, capable of eating practically anything: meat, plants, insects, eggs, whatever was available. Third, and this is crucial, they controlled fire. The oldest evidence of controlled use of fire comes from Homo erectus sites in Africa, dating back 1,500,000 years, possibly even earlier. Controlling fire changed absolutely everything. It meant protection against nocturnal predators. It meant heat in cold climates. It meant light in the dark. And crucially, it meant cooking. Cooking food is perhaps the most important technological discovery in human history. Cooked meat is easier to chew and digest, releasing more calories and nutrients. Cooked plants eliminate toxins and soften indigestible fibers. With cooking, Homo erectus could extract more energy from less food, fueling those increasingly larger brains without needing to spend all day chewing, like modern great apes do. Some anthropologists argue that the control of fire also fostered social development. Fire creates a natural focal point. People gather around it at night, sharing food, telling stories, strengthening social bonds. If Homo erectus developed proto-language, those nightly gatherings around the fire would have been the perfect context for its evolution. Homo erectus tools were also revolutionary, although in a curiously conservative way. They developed what archaeologists call Acheulean technology, dominated by the biface hand axe. These tools were elaborate, symmetrical, clearly standardized. They required planning and skill to manufacture, and strangest of all, they remained practically unchanged for over 1 million years. Think about that. 1 million years with the same basic technology. Homo sapiens went from stone tools to smartphones in only 200,000 years, but Homo erectus manufactured essentially the same hand axe for 1,000 generations or more. Were they extreme conservatives? Did they lack the creativity to innovate? Or had they simply found a technology so perfectly suited to their needs that there was no reason to change it? The answer is probably a bit of everything. Homo erectus was intelligent, but not as intelligent as us. Their capacity for innovation was limited, and they lived in a world where survival depended more on physical endurance and dietary adaptability than on technological sophistication. If your tools worked, if you could get enough food to survive, there was no strong evolutionary pressure to innovate constantly. But here is the deepest mystery of Homo erectus. With all their success, all their longevity, with populations spread across 3 continents for almost 2 million years, they eventually disappeared. And the causes of their extinction are as complex and debated as any mystery in paleontology. The story is not simple, because Homo erectus probably did not disappear all at once. Populations in different regions evolved differently, isolated from each other for hundreds of thousands of years. Some paleontologists argue that the African Homo erectus populations eventually evolved into Homo heidelbergensis, which in turn gave rise to Neanderthals and sapiens. If that is true, then African Homo erectus did not become extinct. It simply transformed. But the Asian populations are another story. The last Homo erectus in Java survived until between 117,000 and 108,000 years ago. That means they coexisted with Homo sapiens for tens of thousands of years. Sapiens arrived in Southeast Asia at least 80,000 years ago, and the two groups likely met. What happened in those encounters? We do not know for sure. There is no clear evidence of direct violence, but we do not need it either. When two species compete for the same resources, and one is cognitively superior, the result is predictable. Sapiens, with more advanced technology, more complex social organization, and possibly fully articulated language, would have been much more efficient competitors. There is another, darker possibility that some scientists consider. Perhaps there was hybridization. Perhaps sapiens and the last erectus interbred, genetically diluting the older species until it ceased to exist as a separate entity. So far, we have not found evidence of Homo erectus DNA in modern humans, but that could simply be because the genetic material is too old to survive in the fossils we have. Climate change also played a role. The last 100,000 years have seen extreme climatic fluctuations. Ice ages that froze vast areas, followed by warm periods that transformed entire landscapes. Homo erectus had survived previous climatic changes, but perhaps the Asian populations, already isolated and with reduced genetic diversity, simply could not adapt this time. And then there is the gloomiest theory of all. Perhaps sapiens did not just surpass Homo erectus, but actively hunted and exterminated them. There is no direct archaeological evidence of genocide, but the absence of evidence is not evidence of absence. Bones do not preserve all stories. Spears do not leave traces after 100,000 years. And we know from our own recent history that humans are perfectly capable of exterminating other groups they perceive as different or threatening. What we do know is that 100,000 years ago, Homo erectus had completely disappeared. After almost 2 million years of uninterrupted dominance, after conquering 3 continents, after surviving countless climatic changes and environmental challenges, the most successful human species that ever existed became extinct. Their legacy is undeniable. They gave us fully developed bipedalism. They taught us to control fire. They showed us that humans could live in almost any terrestrial environment, from tropical jungles to cold steppes. They prepared the evolutionary path that would eventually lead to us. But they also taught us something more unsettling. They taught us that even the most spectacular success does not guarantee permanent survival. That 2 million years of dominance can end in extinction. That being the most adaptable species of your time does not protect you against even more adaptable competitors who emerge later. Homo erectus walked the earth when our sapiens ancestors did not even exist. They saw millions of days dawn, and then silently disappeared into the night of time, leaving only fragments of bones and tools as testimony that they were once the undisputed owners of this planet. In 2008, Russian archaeologists were excavating in Denisova Cave, a remote site in the Altai Mountains in Siberia, when they found something extraordinary: a small fragment of finger bone, barely the distal phalanx of a pinky, so small that it fit in the palm of a hand, so insignificant in appearance that it could easily have been discarded as animal bone. But that fragment would completely change our understanding of human evolution. Scientists extracted DNA from the bone, expecting to find Neanderthal or sapiens genetic material. The only two human species we knew had inhabited that region. What they found left the entire scientific community in shock. The DNA did not belong to Neanderthals. It did not belong to sapiens. It belonged to a completely unknown species, a human lineage that had diverged from our common ancestors more than 700,000 years ago. They called them Denisovans after the cave where the discovery was made. And to this day, almost all our information about them comes from genetic material. We have barely 4 physical specimens: that finger fragment, 3 molar teeth, a skull fragment, and jawbone fragments. That is all. We do not have a complete skull. We do not have a skeleton. We do not know exactly what they look like. They are literally ghosts, known only by the molecular traces they left behind. But those genetic traces tell an amazing story. Denisovan DNA analysis reveals that they were a sister species to the Neanderthals, sharing a common ancestor approximately 400,000 years ago, while the Neanderthals migrated west, dominating Europe and parts of the Middle East. The Denisovans moved east, settling in Central Asia, Siberia, and possibly extending to Southeast Asia and even Oceania. The few physical remains we have suggest some distinctive characteristics. The molars are extraordinarily large, larger than those of any other known hominin, including Neanderthals. The jawbone fragment found in a cave on the Tibetan Plateau, at 4,520 meters above sea level, is robust and massive, with a morphology that does not completely match any other known human species. But the true revelation came when scientists began to analyze the DNA of modern humans. They discovered that approximately between 3 and 5% of the genome of Melanesian, Australian, and Southeast Asian populations comes from Denisovans. That means hybridization. It means that our sapiens ancestors not only encountered the Denisovans, but interbred with them, exchanged genes, and produced viable and fertile offspring. And it was not just an isolated event. Genetic analysis suggests multiple episodes of hybridization between sapiens and Denisovans over tens of thousands of years. Some scientists even speculate that there may have been more than one Denisovan population, genetically differentiated from each other after hundreds of thousands of years of geographical separation. The geographical distribution of Denisovan DNA in modern populations tells a fascinating migration story. The highest populations of Denisovan ancestry are found in Papua New Guinea and Australia. How did genetic material from a Siberian species reach South Pacific Islands? The answer is that the Denisovans probably had a much wider geographical range than the few fossils suggest. They possibly extended from Siberia in the north to the tropical Southeast Asia, adapting to incredibly diverse environments. And here is one of the most intriguing parts. The jawbone fragment found on the Tibetan Plateau dates back at least 160,000 years. At that extreme altitude, with air containing 40% less oxygen than at sea level, survival requires specific physiological adaptations. And it turns out that modern Tibetans carry a specific genetic variant, EPAS1, that helps them survive at extreme altitudes. That variant comes directly from the Denisovans. Think about the implications. The Denisovans not only lived on the roof of the world more than 160,000 years ago, but they developed specific genetic adaptations for that hostile environment. And when our sapiens ancestors arrived on the Tibetan plateau tens of thousands of years later, they inherited those adaptations through hybridization. Denisovan genes literally allowed modern humans to colonize one of the most inhospitable environments on the planet. But there is more. The Inuit and other Arctic indigenous peoples also carry Denisovan genetic variants related to extreme cold adaptation and fat metabolism. The inhabitants of the highlands of Papua New Guinea have Denisovan genes that affect the immune system, possibly providing resistance to local pathogens. In each case, hybridization with Denisovans provided specific adaptive advantages that help sapiens survive in challenging environments. Denisova Cave itself is an extraordinary archaeological site. The stratigraphic layers reveal intermittent human occupation for almost 300,000 years. Denisovans lived there, Neanderthals lived there, sapiens lived there, and astonishingly, there is evidence that the three groups coexisted in different periods, sometimes with temporal overlap. In 2018, scientists analyzed the DNA of a bone fragment from the cave and discovered something that seemed impossible. The bone belonged to an adolescent girl who lived approximately 90,000 years ago. Her mother was Neanderthal. Her father was Denisovan. She was a first-generation hybrid. Direct evidence that these two species did not just coexist, but interbred. This discovery demolished old notions that different human species avoided each other or considered each other too different for mating. The reality was much more complex. Archaic humans, when they met, sometimes formed relationships, produced children, and mixed their genetic lineages. They were not totally separate species in the strict biological sense. They were divergent populations that could still exchange genes. But if the Denisovans were so successful, if they adapted to environments from Siberia to the tropics, if they survived for hundreds of thousands of years, why did they disappear? And when exactly did they become extinct? The dates are uncertain because we have so few fossils. The finger fragment from Denisova Cave dates back approximately 76,000 years. The Tibetan jawbone fragment is much older, 160,000 years. But genetic evidence in modern humans suggests that hybridization continued until as recently as 15,000 or 20,000 years ago in some regions. That would mean that Denisovans survived much longer than the few fossils indicate, that they continued to exist as a viable reproductive population until the end of the last ice age, and that their final extinction could have occurred at the same time that woolly mammoths and saber-toothed tigers disappeared during that period of mass extinctions that swept the Pleistocene megafauna. Theories about their extinction are speculative, but probably familiar. Climate change at the end of the last ice age, transforming landscapes and eliminating food sources, competition with sapiens, who by then already dominated sophisticated technologies and complex social structures, and perhaps in some regions, genetic assimilation, where Denisovan populations hybridized so extensively with sapiens that they ceased to exist as a genetically distinct group. The most frustrating thing about the Denisovans is everything we do not know. We do not know exactly what they looked like. Were they tall or short, robust like Neanderthals, or gracile like some sapiens populations? Did they have prominent brow ridges, wide noses, recessive chins? Scientists have tried to reconstruct their appearance using genetic data and computational models, but they are only educated approximations. We do not know what kind of culture they had. Archaeological sites associated with Denisovans contain stone tools, but they are difficult to distinguish from those made by Neanderthals or sapiens from the same period. Did they have art? Did they bury their dead? Did they have spoken language? Their brain size, estimated at around 1,100 to 1,300 cubic centimeters based on the skull fragment, suggests significant cognitive capacity, but the details remain a mystery. We do not know how many different Denisovan populations existed. Genetic analysis suggests at least 3 distinct lineages, geographically separated for hundreds of thousands of years. Each population probably developed its own adaptations, its own culture, its own physical characteristics. But without more fossils, without more DNA, we cannot reconstruct that diversity. And here is the deepest irony. The Denisovans are the extinct human species about which we have the most genetic information and the least physical information. It is like knowing a computer's complete software without ever having seen the hardware. We know what genes they had, how those genes differ from ours, what specific variants they passed on to modern human populations, but we do not know what their face looked like. They are ghosts in the most literal sense, invisible presences that we know existed because they left traces, but that we can never fully see. And every time a modern Melanesian looks at the mountains of Papua New Guinea, every time a Tibetan breathes the thin air of the plateau, every time any of us carries even a fragment of Denisovan DNA, these ghosts continue to live, hidden in our own genes. In 2003, a team of Australian and Indonesian archaeologists was excavating in Liangbua Cave on the island of Flores, Indonesia, when they unearthed something that defied all evolutionary logic. It was a complete human skeleton, but impossibly small, so small that they initially thought they had found the remains of a child. But dental analysis revealed the astonishing truth. This was a fully grown adult who measured barely 1 meter tall. They named it Homo floresiensis, but the world quickly came to know them by their more evocative nickname, the Hobbits. And that name, although originating in fiction, perfectly captured the extraordinary nature of this discovery. Here was a human species that looked straight out of a fairy tale, so small that an adult sapiens could have lifted it with one hand, and yet it had made stone tools, hunted animals, and survived on a remote island until barely 50,000 years ago. The first skeleton catalogued as LB1 belonged to a female who died approximately 60,000 years ago. Her brain measured only 400 cubic centimeters, the size of a chimpanzee's brain, approximately a third the size of the modern human brain. Her estimated weight was 25 to 30 kilograms. Her arms were disproportionately long. Her feet were flat and extraordinarily large in relation to her stature, measuring 20 centimeters long, almost a fifth of her total height. The discovery provoked a fierce scientific debate that continues to this day. Some researchers argued that LB1 was not a separate species, but simply a modern sapiens suffering from microcephaly or another developmental disorder. But as more fossils were found, at least 14 individuals in total, all showing the same diminutive characteristics, that theory became untenable. These were not abnormal individuals. It was an entire population of miniature humans. The story of how Homo floresiensis came to be so small is a perfect example of what biologists call insular dwarfism. When animals become isolated on islands with limited resources and no major predators, evolution frequently reduces their size. Smaller bodies require less food, a crucial advantage in environments where resources are scarce. This phenomenon has occurred repeatedly in evolutionary history, from pygmy elephants to dwarf hippos. But insular dwarfism in humans was something completely unexpected. Intelligence, after all, was supposedly required for large brains. Everything in human evolution had been a race toward bigger and bigger brains. And here we had a species that had dramatically reversed that trend, shrinking both physically and cerebrally, and yet still clearly human in behavior. The island of Flores, where these hobbits lived, was a strange world, a unique ecosystem shaped by millions of years of isolation. There lived the stegodon, an extinct relative of modern elephants, which had also suffered insular dwarfism, shrinking to approximately the size of a water buffalo. There were giant rats, the size of small dogs. There were Komodo monitor lizards, the largest lizards in the world, which could grow up to 3 meters long. And in the midst of this strange fauna, the small Homo floresiensis hunted, gathered, and survived. Excavations in Liangbua revealed sophisticated stone tools associated with the Homo floresiensis fossils. These tools showed evidence of careful manufacture and standardization. There was evidence of controlled fire, hearths where they cooked their food, and most astonishingly, there were bones of young stegodon with cut marks, clear evidence that these diminutive humans hunted or scavenged animals many times larger than themselves. Imagine the scene: 1 meter tall humans working in groups, using wooden spears with stone tips, bringing down a pygmy elephant that still weighed hundreds of kilograms. It required coordination, planning, communication. It required significant intelligence. How did they achieve it? With brains the size of a chimpanzee's. This is one of the most fascinating questions Homo floresiensis poses. Brain size is not the sole determinant of intelligence. Structure matters. Neural organization matters. The density of synaptic connections matters. It is possible that the Homo floresiensis brain, although small, was organized in an exceptionally efficient manner, compensating in quality for what it lacked in quantity. It is also possible that insular isolation and size reduction occurred slowly enough that natural selection preserved the most critical cognitive capacities while eliminating less essential brain tissue. The result would be a smaller but functionally capable brain, a model of evolutionary efficiency. But here is the real mystery. Where did they come from? What ancestral species reached Flores and then evolved into these hobbits? For years, scientists assumed they must descend from Homo erectus, which we know was in Southeast Asia more than 1 million years ago. Flores is not far from the Asian continent, and during sea level drops in the ice ages, the distances between islands would have been significantly reduced. But more recent analyses suggest something stranger. Some characteristics of the Homo floresiensis skeleton, particularly in the wrists and feet, more closely resemble Australopithecines or even Homo habilis than Homo erectus. That raises the extraordinary possibility that a very ancient human species, prior to Homo erectus, somehow reached Flores 2 million years ago or more, and then evolved in isolation for all that time. If that is true, it would mean that our primitive human ancestors were much better navigators than we ever imagined. Reaching Flores, even with reduced sea levels, would have required crossing at least 19 kilometers of open ocean. You cannot simply walk across the seabed or swim that distance safely. You need some type of raft or watercraft. And traditionally, we assumed that navigation was a relatively recent invention, not something that small-brained hominins could have achieved 2 million years ago. But perhaps we underestimate our primitive ancestors. Perhaps the intelligence needed for basic navigation appeared much earlier than we thought. Or perhaps it was pure luck. Individuals trapped in floating vegetation during storms, carried by currents to distant beaches, accidentally finding a new world they would colonize for millennia. The chronology of Homo floresiensis is equally astonishing. The oldest fossils date back approximately 100,000 years, but stone tools at the same site date back at least 700,000 years, possibly up to 1 million years. That suggests that the Hobbit ancestors were on Flores for an extraordinarily long period, more than enough time for insular dwarfism to produce dramatic changes, and they survived until surprisingly recent times. The last Homo floresiensis fossils date back approximately 50,000 years. That is barely yesterday, in evolutionary terms. To put it in perspective, the oldest known cave paintings are approximately 45,000 years old. When our sapiens ancestors were creating sophisticated art in Europe, the hobbits were still hunting pygmy elephants on Flores. Did sapiens and floresiensis meet? Almost certainly. Sapiens arrived in Southeast Asia at least 60,000 years ago, and Flores is not that far. Some archaeologists speculate that modern humans could have arrived on Flores 50,000 years ago or even earlier. If that is correct, then the two species coexisted on the same island. And then, 50,000 years ago, Homo floresiensis disappears from the fossil record. They were simply gone without a clear explanation. Was it a coincidence that their extinction occurred just when sapiens probably arrived on the island? Some scientists doubt it. Others argue it may have been the result of a massive volcanic eruption, of which there is geological evidence around that period, or climate change, or disease. But the pattern is disturbingly familiar. Around the world, when Homo sapiens arrives in new regions, other human species tend to disappear shortly thereafter. Australia, New Zealand, Madagascar, the Americas, wherever modern humans colonized, local species faced mass extinctions. The hobbits of Flores might have been another victim of this global pattern. Local legends on Flores speak of the Ebu Gogo, small hairy creatures that lived in caves and occasionally stole food from villages. The island's elders insist that these creatures existed until only a few hundred years ago. Are these legends distorted cultural memories of real encounters with the last Homo floresiensis? Probably not. 50,000 years is too long for oral traditions to be preserved accurately, but the stories are intriguing, reminders that the deep past sometimes leaves echoes in cultural memory. Homo floresiensis teaches us humbling lessons about evolution and intelligence. It shows us that brain size is not everything, that intelligence can be packaged in unexpected ways, that humans can adapt to extreme environments in ways we never anticipated, and that even species that seem successfully adapted, that have survived for hundreds of thousands of years in their specialized niches, can become extinct suddenly when conditions change or when more efficient competitors arrive. The hobbits lived and died on their remote island, probably never knowing that a larger world existed beyond their horizons. And for 50,000 years after their disappearance, no one knew that they had existed until a team of archaeologists unearthed their bones and revealed to the world that reality is sometimes stranger than fiction. Of all the extinct human species, none has captured the popular imagination as much as the Neanderthals. For more than a century after their discovery, they were portrayed as stupid brutes, clumsy cavemen, who deserved their extinction in the face of the superior, intelligent sapiens. But every new discovery has demolished those stereotypes, revealing a much more uncomfortable truth. Neanderthals were not inferior to us. In many respects, they were our equals, and in some, possibly our superiors. The first recognized Neanderthal fossil was discovered in 1856 in the Neander Valley, Germany, from which they get their name. But for decades, scientists debated what exactly they were. Some argued they were primitive human ancestors. Others insisted they were simply modern humans deformed by disease. It was not until the early 20th century, when more fossils were found across Europe, that scientific consensus recognized Neanderthals as a distinct human species. Physically, Neanderthals were impressive. Males averaged 1.69 meters tall, females 1.56, slightly shorter than the average sapiens, but considerably more robust. They weighed between 64 and 82 kilograms, with dense muscles and extraordinarily thick bones. Their bodies were adapted for cold climates, with wide, barrel-shaped torsos that minimized heat loss, short limbs that reduced cold exposure, and large noses that warmed and moistened the air before it reached the lungs. But the most notable thing was their brain. Averaging 1,500 cubic centimeters, Neanderthal brains were actually slightly larger than those of the average Homo sapiens, which measure around 1,400 cubic centimeters. That makes them the hominins with the largest brain relative to body size that have ever existed. And contrary to decades of scientific propaganda, that large brain was not just muscle without mind. Neanderthals manufactured sophisticated tools using Mousterian technology, which required complex planning and considerable skill. They controlled fire masterfully, building elaborate hearths that maximized heat and minimized smoke. They hunted dangerous megafauna, mammoths, woolly rhinoceroses, giant bison, using coordinated hunting tactics that required communication and cooperation. And they did not just hunt. Excavations in Neanderthal caves have revealed evidence of deliberate burials with bodies carefully placed in specific positions, sometimes accompanied by tools, animal bones, even flowers. That suggests awareness of death, perhaps belief in life after death, definitely ritual and symbolism. Behaviors that for decades were considered exclusively modern human. They cared for their sick and injured. Multiple Neanderthal skeletons show severe injuries, fractures, infections that healed completely, indicating that the individual received prolonged care when they could not fend for themselves. A specimen called Shanidar 1, found in Iraq, had lost an arm, had severe damage to a leg, was probably blind in one eye, and yet lived to approximately 40 years of age, an advanced age for the time. Someone fed him, protected him, kept him alive for years after he could no longer actively contribute to the group's survival. That is empathy. That is compassion. That is humanity in the deepest sense. Neanderthals also created art, although this was debated for decades. Cave paintings in Spain dating back more than 64,000 years before sapiens arrived in Europe could only have been made by Neanderthals. Abstract engravings on bones and stones, perforated seashells, used as beads, some dyed with red ochre, modified eagle talons, possibly used as jewelry or ceremonial adornments. And perhaps most surprisingly, there is growing evidence that Neanderthals had spoken language. They possess the FOXP2 gene, critical for speech in modern humans, in a form almost identical to ours. The anatomy of their hyoid, the small bone in the throat, essential for complex speech production, is virtually indistinguishable from ours. Their ear canals were tuned to frequencies associated with human speech. Everything points to full linguistic capacity. So, if they were so intelligent, so adaptable, so successful, why did they disappear? Neanderthals dominated Europe and parts of Asia for more than 300,000 years. They survived multiple ice ages, developed complex cultures adapted to dozens of different environments, and then, approximately 40,000 years ago, they began to disappear. The last known Neanderthals lived in Gibraltar around 37,000 years ago, and after that, silence. The chronology is revealing. Homo sapiens arrived in Europe approximately 45,000 years ago. For approximately 5,000 to 10,000 years, the two species coexisted, and then the Neanderthals were gone. The correlation is too strong to ignore. Our arrival and their disappearance are clearly connected, but the connection is not simple. For decades, scientists assumed direct competition and violence. Sapiens, with superior technology and greater numbers, simply exterminated the Neanderthals in a genocidal campaign. But the archaeological evidence does not support that scenario. There are no mass graves, No clear evidence of massive battles. No sites that scream deliberate genocide. Instead, the image that emerges is more subtle and perhaps more unsettling. Sapiens did not necessarily kill Neanderthals directly. They surpassed them. Sapiens had more complex social organization, capable of forming exchange networks spanning hundreds of kilometers. They had slightly more efficient technology, sharper spear points, more specialized tools, and crucially, they had numbers. The sapiens population grew more quickly, producing more offspring, expanding more aggressively. In any competition for limited resources, caves for shelter, animals to hunt, plants to gather, sapiens gradually prevailed, not necessarily through direct violence, but simply by being more efficient, exploiting resources more quickly, leaving less for the Neanderthals. And slowly, over thousands of years, Neanderthal populations dwindled, fragmented, and became isolated in increasingly smaller pockets. Climate change did not help. 40,000 years ago, Europe was entering a period of extreme climatic fluctuations, rapid oscillations between glacial and temperate conditions. Neanderthals, specialized for cold and stable climates, found it increasingly difficult to adapt to these changing conditions. Sapiens, with their more flexible technology and more adaptable social organization, could change strategies more quickly. But here is the final twist in the Neanderthal story. They did not disappear completely. In 2010, the Neanderthal Genome Project revealed that approximately 2 to 3% of the DNA in modern non-African humans comes from Neanderthals. That means hybridization. Our sapiens ancestors not only encountered Neanderthals, they interbred with them, produced fertile offspring, and mixed their genetic lineages. Those Neanderthal genes are not just inert relics. Many are active, influencing modern human characteristics. Neanderthal variants affect skin and hair color, particularly in European populations. They affect the immune system, providing resistance to certain pathogens. They affect metabolism, blood clotting, even predisposition to certain diseases like type 2 diabetes and depression. In a sense, the Neanderthals never became completely extinct. They live in us, fragments of their genome interwoven with ours, molecular ghosts that influence who we are. Every time someone of European descent has red hair, every time someone's immune system fights an infection, every time any of us carries Neanderthal genes, this ancient species continues to exist. But genetic assimilation is also a form of extinction. Neanderthals, as a genetically distinct population, disappeared. Their unique culture, their languages, if they had them, their specific ways of seeing the world, everything was lost. What remains are only genetic echoes, fragments preserved in a species that replaced them. The relationship between sapiens and Neanderthals has been described as an encounter between sister species, cousins who separated approximately 600,000 years ago and then met again in Europe 45,000 years ago. During that reunion, there was cultural exchange, sapiens adopting some Neanderthal techniques, and vice versa. There was hybridization, although probably limited, occasional encounters that produced mixed offspring, and eventually, there was replacement, not through a planned genocidal war, but through the cumulative weight of small advantages. Sapiens were slightly more efficient at hunting, slightly better at large-scale social organization, slightly more adaptable to changing environments, and those small advantages, multiplied over thousands of years, were enough. Neanderthals teach us profound lessons about the nature of intelligence and survival. They show us that being intelligent does not guarantee survival, that having large brains, complex cultures, empathy, and compassion does not protect you against extinction if a slightly more efficient competitor appears. that evolution does not reward abstract moral or intellectual superiority. It only rewards reproductive efficiency in a specific context. And they show us something more uncomfortable. They show us that we, Homo sapiens, are not necessarily the good guys in this story. We are the survivors. Yes, but our survival came at the cost of another intelligent, conscious species, capable of love and art and complex thought. A species that deserved to inherit the earth as much as we did, but that had the bad luck to encounter us at the wrong time in history. The last Neanderthals died alone in Gibraltar, perhaps looking at the same Mediterranean their ancestors had contemplated for 300,000 years, unaware that they were the last of their kind. And, with their death, the evolutionary experiment that created them ended, leaving only fossil bones and DNA fragments as testimony that they once walked among us. In September of 2013, 2 amateur cavers crawled through an incredibly narrow fissure in the Rising Star Cave system, about 50 kilometers from Johannesburg, South Africa. The opening was so narrow that only exceptionally slender people could pass, descending vertically through solid rock, in near total darkness. And at the end of that terrifying descent, in a deep chamber called Denisovans, the Chamber of Stars, they found something that would change our understanding of human evolution. Bones, thousands of them scattered across the chamber floor, accumulated in corners, preserved in almost perfect conditions. And when the paleoanthropologist Lee Berger led an expedition to recover them, when his team began to analyze the fossils, they realized they were looking at something completely new, a human species that no one had seen before. They named it Homo naledi, the Starman. The first analyses revealed a deeply disconcerting creature, an evolutionary mosaic that seemed to defy all the rules of how human evolution was supposed to work. Homo naledi had a tiny brain, between 450 and 600 cubic centimeters, similar in size to that of the Australopithecines, who lived more than 2 million years ago. Their shoulders, pelvis, and some aspects of the skull also seemed primitive, reminiscent of much older species, but other characteristics were surprisingly modern. Their hands were almost indistinguishable from ours, with wrists and fingers perfectly adapted for the precise manipulation of tools. Their legs and feet could have belonged to a modern human marathon runner, long, efficient, designed for walking and running long distances. And their teeth, although small, showed wear patterns consistent with a varied diet similar to that of later humans. It was as if someone had taken parts of different human species, separated by millions of years of evolution, and mixed them into a single creature. And for years, scientists assumed that Homo naledi must be very old, perhaps contemporaneous with Homo habilis, or even late Australopithecines. That would explain their primitive characteristics. But in 2017, the dating results arrived and demolished all assumptions. Homo naledi was not 2 million years old. It was between 335,000 and 236,000 years old. That placed them firmly in the Middle Pleistocene period, an era when large brains and completely modern bodies supposedly dominated human evolution, a time when Homo heidelbergensis, early Neanderthals, and the first Homo sapiens were already walking the earth. How was it possible for a species with an Australopithecine-sized brain to survive until such recent times? How did they coexist with much larger-brained species? And the most unsettling question of all, what were thousands of their bones doing in the depths of an almost inaccessible cave? The Denisovans chamber is not easy to reach. It requires descending through multiple narrow passages, some so narrow that an average adult human could not pass. There is no evidence that it was ever more accessible. There are no collapsed tunnels or now blocked entrances. It was always difficult to reach, and yet, At least 15 Homo naledi individuals ended up there, from infants to elderly, their bones accumulating over what could have been decades or even centuries. There is no evidence that they died there from natural causes. The bones do not show teeth marks from carnivores, ruling out predators carrying them into the cave. There is no evidence that water dragged them there. The bones are not sorted by size or weight, as would happen with hydraulic transport. And most notably, there is practically no other animal present. It is almost exclusively Homo naledi. The most plausible explanation, although also the most revolutionary, is the deliberate disposal of bodies, that other Homo naledi members carried the bodies of their dead to this deep chamber, depositing them there in what can only be described as ritual burial. But if that is true, it completely changes our understanding of when and how symbolic and ritual behavior emerged. For decades, scientists assumed that deliberate burial and ritual behavior required large brains and advanced cognitive capacities. Neanderthals, with 1,500 cubic centimeter brains, buried their dead. Sapiens, with 1,400 cubic centimeter brains, definitely did. But Homo naledi, with brains of barely 500 cubic centimeters, a third our size, also participated in funerary rituals. If the answer is yes, and increasing evidence suggests that it is, then brain size is not the only predictor of complex behavior. Something else is happening. Perhaps the organization of the brain matters more than the total size. Perhaps certain critical brain structures can develop even in small brains. Or perhaps we drastically underestimate the cognitive capacities possible with smaller brains. In 2017, a second chamber was discovered in the rising star system called Lesedi, which also contained Homo naledi fossils. And in 2020, additional analyses revealed something even more extraordinary: evidence of deliberate engravings on the cave walls. Simple but clearly intentional geometric patterns associated with the Homo naledi deposits. If Homo naledi really created symbolic art, even rudimentary, that would place them in a cognitive category previously thought exclusive to large-brained species, and raise fundamental questions about the nature of consciousness and symbolism. Can you have awareness of death with a 500 cubic centimeter brain? Can you conceptualize the afterlife? Can you create abstract symbols? Homo naledi forces us to reconsider these questions, and the answers are profoundly unsettling for our conception of what it means to be human. But if Homo naledi was so capable, why did they have such small brains? One possibility is that they evolved in an environment where resources were limited and large brains, which consume approximately 20% of the body's calories, were a disadvantage. Perhaps they lived in regions where food was scarce and unpredictable, and a smaller but efficient brain was better than a large but hungry one. Another possibility is that they represent a case of convergent evolution, where selective pressures produced similar solutions in different lineages. Just as Homo floresiensis independently developed small bodies on an island, perhaps Homo naledi independently developed small brains in response to specific environmental pressures in South Africa. It is also possible that Homo naledi is not really as recent as the radioisotope dates suggest. Fossil dating is notoriously difficult, and there is always the possibility of contamination or error. Some skeptical scientists argue that the fossils could be significantly older, perhaps more than 2 million years old, and that the recent dates are artifacts of contamination or methodological problems. But multiple independent dating techniques have confirmed the recent ages, and more discoveries from additional sites have strengthened the case. Homo naledi genuinely appears to be a small-brained species that survived until relatively recent times, coexisting with much more cerebrally endowed humans. Did they ever interact with Homo sapiens? The dates overlap. The first Homo sapiens appeared in Africa approximately 300,000 years ago, exactly the same period that Homo naledi was living in South Africa. It is almost impossible that they never encountered each other, but we have no direct evidence of interaction, neither remains of both species in the same sites, nor evidence of hybridization in modern human DNA. So far, attempts to extract DNA from Homo naledi fossils have failed. The hot and humid climate of South Africa is not ideal for the preservation of genetic material. Without DNA, we cannot definitively determine their evolutionary relationship with other human species, nor know if they ever exchanged genes with sapiens or other hominins. What we do know is that they eventually disappeared. There is no evidence of Homo naledi after approximately 236,000 years ago. That places them among the last non-sapiens human species to become extinct, surviving longer than many other branches of the human family tree. Theories about their extinction are speculative. Competition with sapiens is the obvious explanation, especially if the two species occupied overlapping territories. But it is also possible that climatic or environmental changes eliminated the specific ecological niches that Homo naledi exploited, or that geological events or epidemics swept away small and isolated populations. The story of Homo naledi is frustrating precisely because it is so incomplete. Every answer generates 10 new questions. How many other species like them are waiting to be discovered? How many branches of the human family tree do we still not know? And what other assumptions about human evolution do we need to reconsider? For more than a century, the dominant narrative of human evolution was progressive. Brains constantly growing, behaviors becoming increasingly complex, an inevitable march toward modern intelligence. Homo naledi breaks that narrative. It shows that evolution is not a one-way ladder, but a bush with branches growing in all directions. It shows that evolutionary success can be achieved in multiple ways, not only through increasingly large brains. And it shows that even when we think we understand human history, the discovery of a single cave can demolish decades of assumptions. The bones in the chamber of stars waited hundreds of thousands of years in the darkness, guarding their secrets, until finally someone descended through those narrow fissures and gave them voice again. Homo naledi reminds us that Earth still holds countless mysteries, that under our feet, in deep caves and sedimentary deposits, stories of forgotten humanities await, and that every excavation, every discovery has the potential to completely change how we understand who we are and where we come from. Let's go back 600,000 years. Europe is plunged into an ice age. Massive glaciers cover Scandinavia and descend south. Great Britain is still connected to the continent by a land bridge, and in this frozen and hostile world, a robust and resilient human species not only survives, but thrives. This species will become the common ancestor of two of the most important human lineages that ever existed, the Neanderthals and us, Homo sapiens. We call them Homo heidelbergensis, named after the site near Heidelberg, Germany, where the first fossil jawbone was found in 1908. But that simple name hides the monumental importance of this species. Homo heidelbergensis represents a critical evolutionary crossroads, the last common shared ancestor of multiple human lineages. And understanding their history is understanding how the species that would eventually dominate the planet emerged. Physically, Homo heidelbergensis was impressive. Males reached heights of 1.75 to 1.80 meters, females between 1.57 and 1.65 meters. They weighed between 60 and 90 kilograms, with muscular and robust bodies adapted for survival in cold climates. Their brains were large, averaging between 1,100 and 1,300 cubic centimeters, approximately 90% the size of the modern sapiens brain. Their skulls showed a mixture of primitive and advanced characteristics, prominent brow ridges like their Homo erectus ancestors, but flatter faces and more projecting noses like later humans. Robust jaws, but with teeth that were beginning to reduce in size. They were clearly transitional, an evolutionary bridge between the older human forms and those that would come later. And their geographical distribution was extraordinary. Homo heidelbergensis fossils have been found throughout Africa, Europe, and possibly parts of West Asia, from the sands of the Sahara Desert to the frozen steppes of Central Europe. This species demonstrated unprecedented adaptability, colonizing practically all available temperate and cold environments in the Old World. The technology of Homo heidelbergensis was significantly more advanced than that of their predecessors. They manufactured wooden spears with fire-hardened tips, the oldest known hunting weapons. In Schoningen, Germany, archaeologists discovered 8 300,000-year-old wooden spears, perfectly balanced, each precisely carved from a single spruce tree. These were not improvised, sharp sticks. They were sophisticated weapons that required an understanding of aerodynamics, balance, and careful material selection, and they used them to hunt the most dangerous megafauna of the time. Archaeological sites associated with Homo heidelbergensis contain bones of wild horses, giant deer, bison, even straight-tusked elephants. Cut marks on the bones show that they systematically processed these enormous animals, extracting meat, marrow, tendons, and hide. They were not opportunistic scavengers. They were efficient and organized hunters. The control of fire also reached new levels of sophistication with Homo heidelbergensis. Sites in Europe show elaborate hearths built in specific areas of shelters with evidence of careful maintenance and control. Some hearths show rocks deliberately arranged around them to contain the fire and reflect heat. This suggests not only use of fire, but an understanding of basic thermodynamics and architectural planning. But perhaps the most fascinating thing about Homo heidelbergensis is what we cannot see directly in the fossil record, but we can reasonably infer: complex communication, possibly primitive language, with brains almost our size, with complex cultures that required the transmission of knowledge between generations, with coordinated hunting behaviors that needed planning and cooperation. It is difficult to imagine that they did not have some form of spoken language. The FOXP2 gene, critical for speech in modern humans, was likely already present in its modern form in Homo heidelbergensis. The anatomy of their throat and vocal box, reconstructed from fossils, suggests the capacity to produce a wide range of sounds. We cannot know exactly what they said or what their language sounded like, but they almost certainly communicated with words, not just grunts and gestures. Approximately 400,000 years ago, something crucial happened. The Homo heidelbergensis populations began to diverge geographically. The African populations, adapting to warm climates and tropical resources, began to evolve in one direction. The European populations, facing brutal ice ages and different megafauna, evolved in another, and these two evolutionary trajectories eventually produced two distinct species. In Africa, Homo heidelbergensis gradually evolved into Homo sapiens. Brains continued to grow slightly. Skulls became more rounded, with more vertical foreheads. Faces flattened more. And approximately 300,000 years ago, the first fossils that we can definitively classify as Homo sapiens appear in Morocco and Ethiopia. Our lineage had been born. Meanwhile, in Europe, the isolated populations of Homo heidelbergensis faced completely different evolutionary pressures. The winters were longer and colder. The megafauna was different, and these populations developed specific adaptations. Robust bodies, larger noses, metabolisms adjusted for cold climates. Approximately 400,000 years ago, these European populations had diverged enough to be classified as a separate species, Homo neanderthalensis. So, Homo heidelbergensis did not really become extinct. It transformed. In Africa, it became us. In Europe, it became Neanderthals. And possibly, some populations in Asia evolved into the Denisovans, although this part of the story is still debated. This is a story of evolutionary success, not failure. Homo heidelbergensis achieved what few species achieve: adaptation to diverse environments, massive geographical expansion, and descendants who would inherit the planet. Their genes flow in every human alive today. Every thought you have, every word you utter, every tool you use is possible thanks to innovations that Homo heidelbergensis perfected 600,000 years ago. But the transition from heidelbergensis to sapiens and Neanderthals was not instantaneous. For hundreds of thousands of years, there were intermediate forms, populations that showed mixtures of ancestral and derived characteristics. The fossil record is full of specimens that paleontologists fiercely debate, arguing whether they should be classified as late heidelbergensis or early sapiens, or something in between. This ambiguity is not a weakness in our knowledge. It is a reflection of how evolution really works. Species do not abruptly change from one form to another overnight. They change gradually over thousands of generations, with different populations evolving at different rates, in slightly different directions. The categories we use, heidelbergensis, sapiens, Neanderthals, are human labels imposed on a continuous process that recognizes no neat boundaries. A particularly important site for understanding Homo heidelbergensis is Atapuerca in Spain, where thousands of fossils dating from between 600,000 and 400,000 years ago have been found. A specific site, called Cima de los Huesos, the Pit of Bones, contains the remains of at least 28 Homo heidelbergensis individuals. And most extraordinarily, all these individuals appear to have been deliberately deposited there. There is no evidence that they lived at the site. There are no tools, no remains of food, no signs of occupation, only human bones accumulated at the bottom of a 13-meter deep chasm. Among the bones, a single, exceptionally beautiful stone tool was found, a perfectly symmetrical red quartzite hand axe that was clearly never used. Scientists call it Excalibur. The most plausible interpretation is that this represents the oldest known deliberate burial site, that members of Homo heidelbergensis carried the bodies of their dead to this special place, throwing them into the pit, perhaps with funerary objects, like Excalibur. If that is correct, it means that conscious recognition of death, mourning, funerary ritual, all of that emerged 600,000 years ago, much earlier than traditionally thought. But Homo heidelbergensis also faces its share of unsolved mystery. Why, if they were so successful, so adaptable, so widely distributed, did their African and European populations diverge so dramatically? What prevented continuous genetic flow between these groups? Was it geographical barriers, the expanded Sahara and Arabian deserts, or cultural barriers, groups that simply chose not to mix? And there is a darker question. If Homo heidelbergensis in Africa evolved into sapiens, and Homo heidelbergensis in Europe evolved into Neanderthals, what happened to the intermediate populations? There must have been groups in the Middle East, in North Africa, on the borders between these territories. Did they also evolve into distinct species? Did they become extinct? Were they absorbed by neighboring populations? The fossil record of the Middle East during this period is frustratingly scarce. We have fossils that show confusing mixtures of characteristics, specimens that different scientists classify in completely different ways. Some argue that they represent hybrid populations, early encounters between emerging sapiens and early Neanderthals. Others insist they are late Heidelbergensis, who had not yet completed the transition to either derived species. The truth is probably complicated. Human evolution during this critical period, between 600,000 and 200,000 years ago, was not an orderly process of clean divergence into distinct species. It was chaotic, with populations fragmenting, reconnecting, occasionally exchanging genes, evolving in parallel, but not in complete isolation. Homo heidelbergensis left us a legacy that goes beyond genes and fossils. It left us the model of how a species can adapt to multiple environments without losing its fundamental essence. It showed us that diversification does not require the extinction of the ancestor, but transformation into multiple forms, each adapted to different challenges. And it taught us that evolutionary success is not measured only in longevity, but in legacy. Homo heidelbergensis, as a distinct species, existed perhaps only 300,000 years, relatively brief compared to Homo erectus. But its impact was immeasurable, because from them came us. And we, for now at least, are still here, carrying their genes, using their innovations, living the future they made possible. 200,000 years ago, the world was a radically different place than the one we know today. Not because the geography was different, or because the climate was dramatically different, but because we were not alone. In Africa, newly emerged Homo sapiens were beginning to expand from their territories of origin. In Europe, Neanderthals dominated forests and icy steppes. In Asia, Denisovans occupied territories from Siberia to Southeast Asia. In Indonesia, the diminutive Homo floresiensis hunted pygmy elephants, and there were probably other species we have yet to discover. Human populations adapted to specific ecological niches in remote corners of the Old World. It was a diverse planet, a massive evolutionary experiment in different ways of being human. And then, in a geological blink of an eye, that entire mosaic of humanities collapsed. 50,000 years ago, most had disappeared. 30,000 years ago, only we remained, Homo sapiens, walking alone in a world that had suddenly become much emptier. What happened? Why? After millions of years of successful human diversity, after 20 or more different species coexisting in different periods, did only one survive? This is the most unsettling and most debated question in all of paleoanthropology, and the answers are neither simple nor comforting. The most obvious theory, and the most uncomfortable to examine honestly, is that we were responsible, that Homo sapiens, as we expanded out of Africa, approximately 70,000 years ago, systematically exterminated all the other human species we encountered. Not necessarily through deliberate and planned genocide, although that may have occurred in some cases, but through relentless competition for resources that inevitably displaced and eventually eliminated our less efficient cousins. The circumstantial evidence is hard to ignore. Every time sapiens arrived in a new region, other human species disappeared shortly thereafter. Neanderthals dominated Europe for 300,000 years, but became extinct within 10,000 years of our arrival. Denisovans controlled vast expanses of Asia for hundreds of thousands of years, but disappeared when we appeared. Homo floresiensis survived on their remote island until 50,000 years ago, precisely the period when sapiens began to colonize Southeast Asia. Correlation does not prove causation, but it is a very strong correlation, and when you examine the details, the picture becomes even darker. The last Neanderthal refuges were in the most remote and inhospitable regions of Europe, Gibraltar, the Pyrenees, caves in the Balkans, as if they were constantly being pushed toward marginal territories, places where they could hide from sapiens' competition, but where survival was increasingly difficult. What advantages did we have over these other species? It was not brain size. Neanderthals equaled or surpassed us in that. It was not physical strength. Many other human species were more robust and muscular, but we had something more subtle and devastatingly effective: superior social organization and slightly more advanced technology. Sapiens developed the capacity to form massive social networks, groups of hundreds or even thousands of individuals, linked by language, shared myths, systems of commercial exchange. Neanderthals lived in small groups, rarely exceeding 50 individuals. That difference in social scale translated into military advantages, more warriors in conflicts, and economic advantages, access to resources and materials from much wider territories. Our technology was also slightly superior. We manufactured sharper and more efficient spear points. We developed specialized tools for different tasks. We invented the bow and arrow, allowing for distance hunting. We created sophisticated nets and traps. Each individual innovation was small, but accumulated, they made us significantly more efficient hunters than any other human species. And then there was language. Although other species probably had some form of spoken communication, sapiens' language seems to have been qualitatively different. We could talk about abstract things, about past and future events, about things that did not physically exist. We could tell stories, create myths, build group identities based on shared narratives. That capacity for complex symbolic thought allowed us to coordinate actions on an unprecedented scale. But direct competition for resources is only part of the story. There are other explanations, perhaps less dramatic but equally lethal. One of them is disease. When sapiens left Africa, we carried African pathogens with us, to which we had developed some immunity after millennia of exposure. But human populations in Eurasia had never encountered these pathogens. When we mixed, when we traded, when we occasionally interbred, we also exchanged diseases. We do not need to speculate about this scenario. We have perfect historical examples of what happens when human populations with different immunological profiles meet. When Europeans arrived in the Americas, they brought diseases like smallpox, measles, and flu. Native American populations, with no prior exposure or immunity, were devastated. Estimates suggest that up to 90% of the Native American population died from disease in the century after contact, without Europeans necessarily throwing a single shot. The same may have happened 50,000 years ago. African sapiens encountered European Neanderthals, and the diseases we unknowingly carried swept through Neanderthal populations that had no defenses. It would not be deliberate genocide, it would be accidental genocide, but genocide nonetheless. Climate change also played a significant role. The last 100,000 years have seen extreme climatic fluctuations, brutal glacial periods, alternating with temperate interglacials, sometimes changing in only decades. Each change reshaped entire ecosystems, moved water sources, eliminated prey species, and forced massive migrations. Human species specialized for specific environments were hit particularly hard. Neanderthals, adapted for cold, stable climates, struggled when the climate became erratic. Their bodies, robust, perfect for conserving heat, were less efficient when temperatures fluctuated. Their hunting strategies, refined over hundreds of thousands of years for specific glacial megafauna, failed when those animals disappeared or migrated. Sapiens, by contrast, were generalists. We could adapt quickly to new environments, change diets, modify hunting strategies, and develop new technologies. Our strength was flexibility. And in a world of rapid and unpredictable climate change, flexibility was the difference between survival and extinction. But there is a darker theory that some scientists seriously consider: genetic assimilation. Not that we killed other human species, but that we interbred with them so extensively that they ceased to exist as genetically distinct groups. Their genes were diluted in the larger sapiens gene pool until the pure populations disappeared. We know hybridization occurred. Neanderthal DNA in modern, non-African humans is undeniable proof. Denisovan DNA in Asian and oceanic populations confirms interbreeding between species. But the question is, how much hybridization occurred, and what effect did it have on the parental populations? If hybridization was rare, occasional events that produced occasional offspring, then it would not explain the extinction of entire species. But if it was common, if expanding sapiens populations routinely interbred with Neanderthals and Denisovans, then eventually the pure populations would have become increasingly rare. And with enough time and enough gene flow, Neanderthals and Denisovans would have simply genetically merged with sapiens, disappearing as distinct groups. This theory is less dramatic than genocide, but equally terminal. The end result is the same. Only one human species survives, carrying genetic fragments of all the others as silent evidence of what they once were. The truth is probably that all these explanations are partially correct. The extinction of non-sapiens human species did not have a single cause, but multiple ones, different for each species and each region. Neanderthals in Western Europe probably succumbed to a combination of competition with sapiens, climate change, and possibly diseases. Neanderthals in Central Asia were perhaps genetically absorbed by sapiens populations. Denisovans in Siberia could have become extinct for completely different reasons than Denisovans in Southeast Asia. And here is the most unsettling part of this story: how easy it was. 20 different human species, most with large brains, complex cultures, advanced cognitive capacities, species that had survived for hundreds of thousands or even millions of years, species specialized for their environments that had overcome countless challenges, that seemed successful and secure, and all disappeared in less than 100,000 years, most in less than 50,000. In evolutionary terms, that is a blink of an eye, a moment, nothing. And when it was gone, the diversity of humanities, that extraordinary experiment in different ways of being intelligent and conscious, had collapsed into a single surviving species. The term Great Filter comes from the Drake equation and discussions about extraterrestrial intelligent life. It is the idea that at some point in the development of complex intelligence, there is a bottleneck, a filter that eliminates most evolutionary attempts. Perhaps that filter is behind us, the 20 species reduced to one, or perhaps it is ahead, waiting for us. Because if there is one thing we should learn from the extinction of our human cousins, it is that past success does not guarantee future survival, that intelligence and culture do not make you immune to extinction, that when a more efficient competitor appears, when the climate changes too quickly, when diseases sweep away populations, even the most successful species can disappear. Neanderthals learned it. Denisovans learned it. Homo erectus learned it, after almost 2 million years of dominance. And someday, perhaps soon in evolutionary terms, we will also learn that lesson. Unless we are intelligent enough, adaptable enough, careful enough to avoid the fate that consumed all the other humanities before us. There is a moment on every clear night when you look at the sky and realize that the stars you see no longer exist. Their light traveled millions of years to reach your eyes, but the stars themselves collapsed, exploded, turned into cosmic dust eons ago. You are looking at ghosts, luminous echoes of things that died before Earth even existed. And it turns out that the same is true for extinct human species. They disappeared tens of thousands of years ago, but their ghosts are still here, hidden in the most intimate place possible, inside you. When the Neanderthal Genome Project published its results in 2010, it revealed something that many scientists did not expect, and some did not even want to believe. Approximately 2 to 3% of the DNA in modern non-African humans comes from Neanderthals. That may not sound like much, but consider what it means. If your genome contains approximately 20,000 genes, then about 400 to 600 of them are literally Neanderthal. Not metaphorically, literally. They are fragments of genetic code that evolved in Europe hundreds of thousands of years ago, passed down through intimate encounters between our sapiens ancestors and their Neanderthal cousins. And it is not just Neanderthals. Populations in Melanesia, Australia, and Southeast Asia carry up to 5% Denisovan DNA. Some scientists speculate that there may have been hybridization with other now extinct species, whose names we do not even know. Ghosts within ghosts. Layers of forgotten ancestors interwoven into our genetic structure. These genes are not inert relics. Many are active, influencing physical and physiological characteristics in modern humans. Neanderthal variants affect skin and hair color, particularly in Europeans. Some light-skinned Europeans owe that trait directly to Neanderthal genes that evolved as an adaptation to low ultraviolet radiation at northern latitudes. Red hair, that distinctive color that appears more frequently in northern European populations, also has Neanderthal genetic connections. The modern human immune system is strongly influenced by archaic genes. When sapiens left Africa and encountered new pathogens in Eurasia, diseases against which we had no defenses, hybridization with Neanderthals and Denisovans gave us instant access to genetic variants that had evolved over hundreds of thousands of years to combat those specific pathogens. Those genes literally saved our ancestors from epidemics that might otherwise have wiped them out. But the archaic inheritance is not all positive. Some Neanderthal variants increase the risk of type 2 diabetes, one of the most common metabolic diseases in modern populations. Others affect blood clotting, increasing susceptibility to thrombosis. Neanderthal genes have been linked to an increased risk of depression, nicotine addiction, and certain types of allergies. Why did natural selection not eliminate these harmful genes? Because evolution is not perfect. It works with what it has available. And, in the specific context of 50,000 years ago, some of these genes probably provided advantages that outweighed their disadvantages. A gene that increases blood clotting is bad in the modern world, where people live for decades with rich diets and little exercise. But in the ancient world, where traumatic injuries were common and the ability to clot quickly could be the difference between life and death, that same gene was advantageous. The Denisovans left a particularly fascinating legacy. The pass, one gene variant that allows Tibetans to live at extreme altitudes, comes directly from Denisovans, who colonized the Tibetan plateau more than 160,000 years ago. Without that gene, modern Tibetans would suffer from chronic altitude sickness, making permanent life on the roof of the world virtually impossible. Denisovans literally gave us the keys to colonize one of the most hostile environments on the planet. Inuit and other Arctic populations carry Denisovan genes related to fat metabolism and thermoregulation, crucial adaptations for survival in extremely cold climates. Melanesians have Denisovan variants that affect the immune system, providing resistance to specific tropical pathogens. In each case, hybridization was not just random genetic exchange. It was the transfer of evolutionary adaptations that took hundreds of thousands of years to develop. Think about the implications. When our sapiens ancestors arrived in new environments, high mountains, Arctic deserts, tropical jungles. They encountered human species that had already spent hundreds of thousands of years adapting to those specific conditions. And instead of competing only through violence or displacement, they sometimes interbred, and those matings allowed the instant transfer of genetic adaptations that would otherwise have taken tens of thousands of years to evolve independently. In a very real sense, hybridization was our superpower. It allowed us to colonize the entire planet in only 60,000 years, an astonishingly short time in evolutionary terms. And we did it not only through our own intelligence and innovation, but also by brazenly stealing the evolutionary adaptations of the species we encountered and partially absorbed. But here is the unsettling paradox. At the same time that we were acquiring useful genes from Neanderthals and Denisovans, we were also eliminating them as genetically distinct populations. Hybridization worked in two directions. Sapiens genes flowing into Neanderthal populations, diluting their genetic distinctiveness. And with enough time and enough gene flow, the lines between species became blurred until only one remained, carrying genetic fragments of all the others as silent evidence of what they once were. It is assimilation, not annihilation, but the end result is the same. The other species disappeared as distinct groups, surviving only as genetic fragments within us. Scientists continue to discover more about these archaic genes. In 2019, researchers identified DNA fragments in modern humans that do not match known Neanderthals or Denisovans, suggesting hybridization with at least one more archaic species, something that lived in Africa and mixed with our ancestors before the migration out of the continent. We call them ghosts because we do not have fossils. We do not have names, only these genetic traces that prove they existed. How many other human species left genetic traces in us? How many more ghosts are waiting to be discovered in the depths of our genome? Every year, genetic analysis techniques become more sophisticated, capable of detecting increasingly smaller and older fragments of hybridization. And every year, the picture becomes more complex. The simple narrative of human evolution sapiens evolving in Africa and then expanding to replace all other species is dead. The reality is much more complicated, much more intertwined. We evolved in Africa, yes, but then we mixed extensively with multiple archaic species in multiple regions, and those genetic mixtures changed us, gave us new capacities, new adaptations, new vulnerabilities. In a very real sense, modern humans are not purely Homo sapiens. We are hybrids, genetic amalgams of multiple human lineages. Africans are mainly sapiens, with touches of unknown ghost species. Europeans are sapiens with Neanderthals mixed in. East Asians are sapiens with Neanderthals and Denisovans. Melanesians and Australians have the most complex mix of all: sapiens, Neanderthals, Denisovans, and possibly other now extinct archaic species. So, when we ask why only we remain, the question itself is flawed. Not only do we remain, all human species are still here, recombined, remixed, fused into a single hybrid species that carries the genetic legacies of 20 different evolutionary lineages. But that does not make the extinction of distinct species less real or less tragic. Neanderthals, as a people, as a culture, as a unique way of being human, disappeared. Their languages, if they had them, were lost. Their stories, their beliefs, their ways of seeing the world all gone. What remains are only genetic fragments, code without context, molecular instructions divorced from the minds that once generated them. And that raises deep philosophical questions. If part of you is Neanderthal, are you responsible for their extinction? If you carry Denisovan genes, are you partially Denisovan? Where does one species end and another begin when genes flow freely between populations? The answers are not clear because evolution does not respect the neat categories that humans prefer. What is clear is that we carry the past with us, literally. Every cell in your body contains messages from ancestors who lived hundreds of thousands of years ago, who faced challenges we can barely imagine, who survived long enough to reproduce and pass their genes to the next generation. And eventually, through uninterrupted chains of descent, spanning thousands of generations, those genes reached you. You are a living mosaic of evolutionary experiments. Part of you evolved on the African savannas. Part of you evolved on the icy steppes of Europe. Part of you evolved in the mountains of Central Asia. And all those parts, all those separate evolutionary stories, converge in the single genome that makes you, you. The extinct human species did not truly leave. They transformed, they fused, they recombined. And the result of that fusion is us, Homo sapiens, in the taxonomic sense, but something more complicated in the genetic sense. We are the sum of everything that came before, carriers of a legacy that spans millions of years and 20 different species. But with that legacy comes responsibility. If we are the only survivors, the only ones who carry the genetic stories of all the extinct human lineages, then we have an obligation not to waste that inheritance, not to become the 21st human species, to become extinct, to use the intelligence, the adaptability, and the accumulated knowledge we inherited from all our ancestors to ensure that this extraordinary fusion of humanities survives. Because if we fail, if Homo sapiens disappears, it will not just be one species that becomes extinct. It will be the combined genetic legacy of 20 species, millions of years of evolution, countless experiments in intelligence and consciousness, all lost in a moment of carelessness or arrogance. The dead stars still shine in the night sky, their light traveling through the void for millennia, and the extinct human species still live in us, their genetic code flowing through generations. Both are ghosts, echoes of things that no longer exist in their original form. But both are real, both have power, both affect us in profound ways. The question is not why only we remain. The question is, what will we do with this extraordinary inheritance, this fusion of 20 humanities into one? Will we honor it by surviving, adapting, evolving? Or will we waste the legacy of millions of years, becoming just another chapter in the long history of intelligent species that reached great heights and then disappeared? The future is still unwritten, but the past lives in every cell of your body, whispering stories of survival against impossible odds, of adaptation to brutal environments, of intelligence slowly emerging from evolutionary chaos. Those whispers are your heritage. What you do with them determines whether human history continues or whether it ends, like so many stories before, in silence and extinction. The ghosts in your DNA await your decision, and they wait patiently, because they have all the patience of evolutionary time, all the persistence of genes that survived millions of years to finally reach you. Do not disappoint them. Do not be the last chapter in their story. Be the next, and make sure there are many more chapters to follow. If you enjoyed this journey through the lost humanities, if these ancient mysteries captured your imagination, consider subscribing to Dato-Terra, because there are countless other secrets buried in Earth's history, waiting for someone to discover and share them. Which mystery of the extinct human species fascinated you the most? The Neanderthals, with their ritual burials, the tiny hobbits of Indonesia, the genetic ghosts of the Denisovans? Leave a comment, sharing your thoughts. Like this video, if you learned something new, and turn on notifications, so you do not miss the next explorations of the deepest mysteries of our planet and our species.